Number 53. Urea, which is NH2, is manufactured on a large scale for use in producing urea-formaldehyde plastics and as a fertilizer. Fun fact. What is the maximum mass of urea that can be manufactured from the carbon dioxide or CO2 produced by combustion of 1.00 times 10 to the third kilograms of carbon followed by the reaction? And then they give us this reaction right here. So in this case, we have carbon dioxide, which is CO2 gas, plus ammonia, which is NH3, right? And this will produce out urea and then water. Okay. So, let's see. If we just rewrite this formula, right, which is just what I said, so I will go pretty fast. Now, when I write my balanced equations, I don't care about the states, okay, because it's just a mess. And you don't need to know your states unless there's like two things of the same thing and one is a liquid and one is a solid. But if they're all different, I don't really write the states. Okay, so we have this, and then we have plus H2O. Okay, now if you guys been with us and on the playlist, right, and you guys already been doing tons of stoichiometry problems, you know that I like to write out everything underneath the compound that is given. I like to just keep everything nice and neat, just so that, it's just easier to see. Now, they're asking for, what is the maximum mass of urea? Now, this maximum mass is a pretty cool topic. This is basically the theoretical mass. If something is theoretical, it means that it's only on paper and on paper only. I think I just said the same thing twice, but who's paying attention? I know you guys are, right? So a theoretical mass is basically the maximum amount of mass that you can produce of whatever you're trying to produce if nothing goes wrong. But we live in an imperfect world, right, where there's errors. So in theory, we'll never be able to produce the maximum amount of mass. But that's what they're asking for here. And we're going to get into theoretical mass later on in this chapter, so hold on tight. But in this case, we're asking just for the mass of the urea. So for the urea right here, I'm just going to say that I'm looking for the mass, and that's grams, right? So, and actually I'm going to put this in blue. Right? So grams equals question mark. But now let's see, which one out of the other three did they give me information from? Well, here's the number. They gave me 1.00 times 10 to the third kilograms of carbon. Say what? Carbon is just C. But there is no compound here, or molecule, that has just carbon in it. What? But they gave us other information. They said that the CO2 is going to be produced by combustion of this amount of carbon. So hold the phone. We have another reaction, right? We have a combustion reaction. This is not a combustion reaction, right? The reason why I know it's not a combustion reaction is because it doesn't have the telltale sign of plus O2 yields CO2 and water, right? So I have to make up my own combustion equation. Now, in this case, they're telling us that we're starting with carbon. Carbon is being combusted. So it's just 1C. And since it's combustion, it's plus O2. And that will yield out the carbon dioxide produced, CO2. Now, I don't say plus H2O because there was no hydrogen on this side. Right? Usually you'll have a hydrocarbon, but in this case you just have carbon, so I can't have the water being produced. Now, this is what we're starting with. We have 1.00 times 10 to the third kilograms, and actually maybe I'll write this in red. So I have 1.00 times 10 to the third kilograms of the carbon. But now with stoichiometry, I can only find out, information on the compounds of the same balanced equation. I can't just zoom up here, even though this is what I want. But we gotta look closely. what is the relationship between this and this? What is the compound that is in both of them? You could pause the video and take a couple of seconds, but the only compound that's in both of them is CO2. Ah, that's how they're linked, right? I can find out the grams of this compound, the CO2, and then that's my starting for the next set. So this is actually a double stoichiometry problem. So the first thing I'm going to have to do is I'm going to have to work on the bottom equation to find out how many grams of carbon dioxide I had. Now, there's a flow diagram for stoichiometry, right? Which I highly recommend you guys memorize. It's this, right? Grams to moles to moles to grams. Grams to moles to moles to grams. So the red, or the A, is what your starting material is, or the number that you started with, and the B's are what you're looking for. So in this case, I'm looking for carbon dioxide first, because then I can link it to this top one. So pretend like this one isn't here for now. We first have to work with the bottom equation. But I'm starting with grams. Oopsie, I have kilograms here. So the first thing I have to do is I have to convert kilograms into grams. How do I do that? Oh, well, all you got to do is just kilograms to grams. We know this conversion. You just times it by 1,000. So technically this is 1,000 already, right? 1 times 10 to the third. So all I have to do is times that by 1,000, and I get 1 times 10 to the 6, right? 1, 2, 3, 4, 5, 6. Yep. So this is the same thing as 1.00 if we keep the sig figs times 10 to the 6 grams. And that's the number that goes in the beginning. Okay, and now it's not A anymore. It's C, right? So I can go from grams of C to moles of C. And then from there, I'm going to go to the compound that I want. In this case, it first has to be carbon dioxide before we move on to the other one. Okay, so maybe I can move this up even a tad bit more. There we go. And let's do the first dimensional analysis on the bottom. Start with what you're given. We always start all the way over here, right? So 1.00 times 10 to the 6, and that's grams of carbon. Now, this is just flowing, right? We're doing ratios. So I don't want this unit. I times by a ratio. You put the unit that you don't want on the opposite side. So in this case, it's grams of carbon on the bottom. And just look ahead to just see what's going on the top. In this case, it's moles of carbon. But remember, what conversion is this? Well, it's a gram to mole or mole to gram conversion of the same thing. We've done this time and time again. This is the periodic table conversion, right? And when you're using the periodic table, you always have 1 mole. So wherever the word mole is, you put a 1 there. The number on the mass on the periodic table goes with the gram value. So in my periodic table, carbon weighs exactly 12.1. Cross off the units that cancel, and now I'm here. But I need to get to, grams of carbon. But we can actually say, hold the phone, and we basically just need one piece of information from the CO2. If you wanted to go to grams of carbon, grams of CO2, that's fine. But I just want to show you other, different things. All we just need is one amount, right? That I can now relate back up to here. So keep going. I don't want moles of carbon. That goes on the bottom. And what I want is moles of CO2. Okay, so units are there, but now the question is, what are the numbers that go on the top or the bottom? This is a mole to mole conversion of different compounds or elements. This is the balanced equation, the BE. In this case, you're looking at the balanced equation that you got your numbers from, and you're just taking the coefficients. That's how these are related. I only care about carbon, and I only care about CO2. But for both of them, there's no number in the front. Oh, that means that there's ones here. So for every 1 carbon, I'm going to produce out 1 CO2. That was pretty simple. Moles of C cancel. And now let's find out how many moles of carbon dioxide is needed. So 1 times 10 to the 6th divided by 12.01. And I get a huge number. Let's not round it too closely. So I'm just going to say 83263, and then I'll say 0.9, because this technically isn't the final answer. We only round with sig figs with our final answer. And this is moles of CO2. Okay. Now this is the starting material that I now can use for the equation that I really wanted in the first place. So I'm going to say that I have 83,263.9 moles of this. And I just want to make sure, 83263.9, yep. And now I can convert to the grams. So what I'm going to do, pause the video if you need. But I'm just going to erase all of this other stuff because we just need to write it down again, right? So bye-bye. It makes me so sad. But now we're using this, right? Now bring back that flow diagram, boop, right? And we're just going to now cater it to what we want. But in this case, since we're starting off with moles of the CO2, I'm already at this stage, right? So I can say, oh, I don't even need this. Bye-bye. That was fun. And now I'm starting with 83,263.9 moles of CO2. I want to get to urea, right? So I'm just going to pull this out a little bit. I think that's good enough. And I want to convert to urea, CONH2, and then CONH2. Okay. So this is 2 steps. So start with what you're given. 83,263.9 moles of CO2. Make that ratio, because we're going now to moles of urea. Moles of CO2 on the bottom, and the moles of urea on top. Okay, cool. Now, look at what type of relationship is this. This is a mole to mole of different compounds. We saw one of those just a couple of minutes ago, right? If it's a mole-to-mole relationship of different compounds, that's the balanced equation. There's only 2 options here, guys. Balanced equation or periodic table. Periodic table has to have a gram in it. Since it's just mole-to-mole, it's got to be the balanced equation. And then we do the same thing. Only look at the coefficients of the compounds that we have here. But for CO2, I don't see a number, so that's a 1. And then for urea, I also don't see a number, so that's also a 1. Okay, units cancel. And now I'm here. We want to find out the mass, so we got to find out those grams. So put the unit that you don't want on the bottom, right? Moles of CONH2, 2, and then the grams of CONH2, 2 goes up on the top. Now look at the relationship. It's a gram to mole of the same compound. Oh, that's the periodic table. And remember, when you're using the periodic table, find the mole, 1 mole. The mass goes with the gram. So I'm just going to count up what the mass is on the periodic table. Keep in mind that you have 2 nitrogens and 4 hydrogens, right, guys? So let's see. I got 1 carbon, so 12.01. Plus 1 oxygen, so 16, plus I have 2 nitrogens, so 2 times the 14, and then I have 4 hydrogens. Okay, and I get 60.062. So maybe if I can just like move this a little bit. 60.062. Cancel those units that are allowed to cancel. Don't cancel the numbers. And now we can finally calculate. Literally, it's just, this number times this number, right? Because all the other ones are ones. So that mass times the 83,263.9. And I just want to make sure I wrote this right. 8326, perfect. Okay, huge number, right? But I'm going to put it into 3 sig figs because we had 3 sig figs all the way in the beginning. Remember, if you're converting, those conversion factors have nothing to do with significant figures. It is only the number that they gave you. So if you started with 3, you got to end with 3. So I'm going to say 5.00 times 10 to the 1, 2, 3, 4, 5, 6. Oh, that's a pretty nice number. And that's grams of the urea. Now, they didn't specifically say whether they wanted this in grams or in kilograms, right? But since they gave us to us in kilograms, probably they're looking for kilograms. But we know how to go from a gram value to a kilogram value, right? All we have to do is just divide by 1,000. So take this number and divide by 1,000. So I'm just going to say that this is the same as 5.00 times 10 to the third grams of urea. And that is also an acceptable answer. So that's it. There you go. Guys, what do you think? Hopefully this helped. This one was a little tricky because you had to do 2 equations and you had to link them together. That's the first time that we see that in this case, but I'm glad we did it, all right? So that you guys won't be stumped on your quizzes or tests. Keep studying hard. I'm so proud of you. This is one of the hardest parts of chemistry, so once we get over this hump, everything should be flowing better, but it's this idea of converting. But I believe in you guys, okay? Keep working hard. Keep studying from the playlist because I'm here with you every step of the way. All right, I'm so proud of you guys and your success thus far. Let's keep going, all right? I'll talk to you in the next lesson. Bye-bye.